Good evening mga Bisaya. So in this video we will be discussing we'll just talk about like really quick about snow load before we proceed with funding load and then wind load and then we'll just talk really quick regarding snow load and snow drift and then seismic load. So because these calculations are repetitive, like in every project you have to do load calculations. So I usually um when I work on a project, if I don't have a spreadsheet, then I will create the spreadsheet first. So when I started working here, I'm trying to develop my own spreadsheet, and so this is basically all you have to do on this one is um, just input the location reference, and then this is the province, and then the town, or for example this is if this is in British Columbia, then say um, let's say West Vancouver. So this one here, so this is the snow load in West Vancouver, like 2.12. So the ground snow load is 2.4. Roof snow load or rain load is zero point 0.2. Associated rain load is zero point 0.2. And then the roof snow load is 2.12 kPa or 44.3. And then this case 2 on left and case 2 right, this is basically if you have, because this is a monoslope. Is this a monoslope? Yeah, or flat roof. Then you have case two and case one and case two only applicable. So there are conditions. So the it's no lo- this case two is for the unbalanced loading. So when you design a, for example, a pre-ins building. So for example, this is a pre-ins building or any building. You have to consider the you know, full snow load, and then the next would be the balance or the unbalanced loading. So it's either this one is full and then this portion here is half, or vice versa, depending on, like for symmetrical building, it doesn't matter because it will be the same whichever is the, you know, load, partial loading if it's left or right. But if the structure is like unsymmetrical, then you have to really be careful with, the unbalanced loading. Now, all this information you can get from so this is the National Building Code, and this is the calculation. This is the formula for getting the roof snow load. So you have the importance factor, the ground snow load, and then all these factors here: exposure factor, slope factor, and then you have these associated rain load. And then all this is R and is S. This is the ground snow load is S, and then is R is the associated rain load. You can get that from the climatic data. What's the page 650 of the National Building Code? So this one here. So this is, you have here on the leftmost column, you have all the we have all the what do you call this one? The province here, British Columbia, and the city, not all cities or towns are in here. So sometimes if all you have to do, for example, the location is not exactly where like these listed towns here, then what you can do, what like in my calculation, so all I have to do is like input here. Now, if it's not like or the location, the exact location is not in here, then all you have to do is look at the map because I link this to a map, and then find wherever, like say for example, um, where is West Vancouver? So it's in this area. So for example, it's somewhere here, which is not um in the list in the National Building Code. All you have to do is just locate where is the nearest location where the data is available, and then for example, this area here. Let's try another location. So for example, this Port Douglas, and then the exact location is Tipila. So I will look for information, and then if this is the closest location where you have information, where you have data in the building code, like this appendix C, then I will use this one. If not, then sometimes I will look the information, the website of the town or municipality, and then they have like a bylaw, and then sometimes they specify their own snow load, wind load, seismic informations like that. Then so all I have to do in my spreadsheet is I will just check or determine the province and then the location, and then information here. This is not part because this is for the energy um requirements calculation. So this one is 2.4. So that's the West Vancouver 2.4, and then SR is zero point 0.2. So it should be in West Vancouver, Vancouver West. This one here. So snow load, it should be here. So this is the SS and SR. Then West Vancouver is this one, 2.4 and point. So I put all these informations in this spreadsheet, and then basically all you have, so I don't have to look at the table again like every project. So I created this one, and then all you have to do is select the location and then the building information here. So this one here, if like I said, if the location is not specified here, so you have user values, for example, this one user values, and then this is also user values. Then in this way, see this site specific is unknown because there's no information. Then you type the actual or whatever is the information for that particular location, and then yeah, once you select this one, it is automatic in the calculation here in the summary, where you have the provinces user values, location user values, and then whatever you input 2.4 and point 0.4. That's exactly these values here. But if you have, like I said, say British Columbia, and this is um where's it? West Vancouver. So that's 2.4 and then point 0.2. Then you go to your calculation. So this is 2.4 here and point 0.2. Then the roof snow load is 2.12. And then the same goes with the seismic. So for the seismic information, so we have the building here, and then I have here like since I don't have the because I we never had a project yet in lower like Vancouver in or lower BC and Vancouver, like Vancouver, West Vancouver, like Richmond, in that area. So I don't have information yet because every time if I do some project and then if it's not in here, then that's the only time, I input all the information because that's a lot of information to input like here, you know. So these locations with already available informations for the seismic, that means we already have project at that location. So, so this one here. So for the sake of discussion, um, we will like in my input, I also have like an option here for like input user values. So for example, like I said, the same situation, if there is no information in the or this is different, by the way. The 2020 is different. All this information is you can get from the hazard tool. So this one here. So for example, this is in BCC 2020 because 2025 is not yet in effect. So 2020 and then say site plus say D and then location. Just type the location. West Vancouver, search address. You have to make sure that's the correct location because sometimes names are the same. So if, for example, this is supposed to be West Vancouver, but for some reason this is in Montreal, West Vancouver, British Columbia. Search address. So this is correct now. So this is the correct location of Vancouver. And then just once you select the correct location, then just check or click the obtain, seismic information. So these are the information that you have to input in the spreadsheet. But like I said, we haven't had a project in Vancouver, so that is blank. So that's why there's no information here. But you can, input like the values here as well instead of going to the this main list here. But yeah, for the sake of discussion, we'll just select user value so that we can use this information here. And then if you go to the seismic, this one here says seismic load calculation. By the way, this is equivalent static force method. There are qualifications when you can use this method. You should check your local governing code. Make sure you have all the information. Like you have to determine if which like if um equivalent static force method is allowed or um so this is a check here, analysis procedure check. So it means here it is PF or ESFM is allowed. And then it will also show like category because this is one um, part that you have to determine what seismic category so that you will know any restrictions. But for this particular location sample, so everything is permitted. Equivalent static procedure is allowed. And then so this is for some reason this is still most Joe Saskatchewan. Is this in most Joe? Oh, because this one here. This is supposed to be British Columbia, and this is West. So I have all this. I have a separate here the province and town, and then this location reference. Because, like I said, sometimes for wind loading, the information is not listed. Then I will use, I will type the reference, the nearest location that has available information. So in that particular where's the seismic. So for the seismic load equivalent static method, so the design base here is 0.024 kilonewton. So that's 0.024 times whatever is the weight, because I set the weight here to 1 kilonewton. So multiply that whatever is the actual weight times 0.024. So that's your base here. And then, so yeah, and then this one, this is also a sample calculation. I already posted a video regarding seismic restraint for ceiling. So this is the calculation that I use for calculating for the base shear or the seismic shear for the seismic force for the ceiling. So this is all the informations from the input, but all you have to do here is this blue one is you have to select the actual height of the ceiling from the ground. And then this one is the category. So you have architectural, structural, mechanical, electrical. I just separated this because this is how it is presented in the building code. And then the category, which category, and then the description. So that's suspended ceiling. And then the base here is because there is no information on this one. Like I said, let's go to user values. How come it's not showing? British Columbia, Vancouver. Why it's not applicable? Normal. There must be information that's missing in the. But you have the seismic acceleration, spectral acceleration already. I don't know why it's not showing. Let me just double check this one here. Category 4 not applicable. Mm-hmm. I don't know what's going on in here. Why is not applicable? It's supposed to be a. So for example, let's try British Columbia. Let's see the St. John. I think I have been no, ano, specify location. I don't know what's going on here. Why it's not showing? Anyway, I will have a look on that one. For some reason, for this particular um um, calculation is not working. But anyway, that's how I calculate for the base year. Or I'm not sure if this is the updated one because I keep on updating my spreadsheet, and this is in my local drive in my computer um, at home, and then all my updated calculation is in the office. So maybe this is the old one. I'm not sure. But anyway, so this is also the wind load, but we will discuss this separately, like the wind load. We'll just focus first on the um, snow load, and then seismic load, and then ponding load. These one are just basically all you have to do is like this one here. It's all in the code. Just follow the code, and you will get the. It's the same in any jurisdiction. Just follow the follow the building code, and every code has a procedure on how to calculate for the snow load and seismic load as well as wind load. But we'll focus on the funding load on this particular video. But at least you have an idea how to get the information. So this one, let's just close this. Now let's go to funding load. This one. Now um before um I used let me I think I already closed. There's a like a really complicated calculation for funding load. And then um basically when I arrived here in 2010 and then started working at the company, um because I have no experience with Canadian code. So I bought a book. It is called um I think it's structural design or Canadian building, I think book. This one. So I bought this book. So new. It's not really that expensive. This one is just 56 to $74. I think the 56 for the used one, and 56, and then the new is this one. So I have this book, and then in this particular book, like there are practical solutions that's really like simple. So there is an explanation regarding how to calculate funding load. So instead of the very complicated, because you have to do like several iterations, because so you have so for example, you have the building, right? For this is the frame, and then for example, you have an interior frame, and then this is the direction of your joist. So if you look at this elevation, it will look like this one, and then it is slopes towards the center, and then you have your beam there. So assuming this is intermediate beam, and then you have columns like that. So for example, that's our column layout for the sake of discussion. So that's the column layout. Now you have to calculate the funding load. So usually the architectural drawing will show how this is sloped. So most of the time it will be sloped like that. So this one it goes in that direction, then this one goes that way, this one is sloped that way, and this one is sloped that way. Now in that book, the calculation is because, for example, you have the initial, because in the climatic information you will get the maximum precipitation in one day. And then it is the information there, the value is in millimeters. So for example, um, wherever, for example, where I am now, say the maximum daily precipitation is 89, I think 89 millimeter. So that's the height of the water, like maximum in a day per hour. So once you have this information and then, calculate the area. So once you calculate the area, you have all the volume. Now that volume, it will cause a what we call this one, a deflection of your beam, right? It will cause deflection, and then every time it causes deflection, the volume will accumulate, and then you will have larger volume now. Then the total volume of water will increase until it reaches the maximum deflection, like the actual deflection. But in that book, the solution is quite simple and really practical. So in that book, he said, instead of calculating, deep, repetitive, like, iterations, what's the maximum, all you have to do is get the maximum deflection of this beam, maximum deflection of that joist, for example, this beam. So you have a height difference of, because this is the roof, right? And then this is the slope. Say for example, this is high point and this is low point of your roof. And then say this is 6 inches difference. Now you have a volume of your water now, that one. But once this beam deflects, so basically all you have to do is a beam, for roof beam, for example, your maximum deflection is L over, say, 4 L over 240 for the sake of discussion, or L over 180. It depends, whatever is the minimum or maximum deflection. Now you have information of this span, right? So for example, this is 20 feet, 20 feet. So therefore, your maximum deflection for this beam at the center, y is equal to 20 feet divided by 180. So whatever this, for example, what's the result of that one? Uh, 20, 20 times 12 divided by 180, 1.33. So this is 1.33 inches. So therefore, your maximum height difference here, right? Maximum height difference is what do you call this one? Maximum height difference is 1.33 plus 6. So this will become now 7.33. So this will be your maximum height. Now to get the volume, so to get the total volume, because you will assume also the worst case scenario in here is your roof drain will be clogged, you know. So it will be clogged. Then water will accumulate instead of the water draining to your downspout. Since the roof drain is clogged, so water will accumulate here. And then usually in this scenario, you have what we call this one. You have a scupper. So you have a scupper. Now, if, for example, this one is your parapet and then this is your roof, usually this is the part that you have to coordinate with the architectural. What would be the scupper height, above the high point here? So, for example, if the architect says our scupper would be at this flush with the high point, but sometimes it is 1 inch, 2 inches above the high point. But for example, the architect would say my scupper would be flush. The scupper would be flush with the high point. Now, remember in fluid mechanics, there is this thing called surface tension, right? So there's that surface tension. So for example, this is the roof, no, roof section, and then this is your scupper. This one, that one. Now the water will not flow at exactly this height here because there is a surface tension, and then I think in Canadian code, if I remember correctly, this is 30, no, 30 millimeter above this um what is called like invert. Is it invert? This, so you have your scalper rectangular. So if this is the lowest point of your opening for the scalper, this is 30 millimeter. So that's 30 millimeter before the water actually starts to flow. That is surface tension. Now, if that's the case, 30 millimeters, so you already have 7, right? 7.33 here, and then you add the 30 millimeter in, convert that into inches, then you have your total. So 30 millimeter is what, 25.4 is, so 1.25. So this will be like around 8 point, close to 8.5. So close to 8.5. So that would be your lowest, um, that would be your lowest elevation or height or depth of your water. So that means in this particular area, so because this is sloping this way, the area here would be different, but this area and this area is the same, and then this area also and this area as well. So basically you have like a triangle, but this one is from 0 to 6, because this one, the deflection here, you can assume that the deflection here is 0 because that's where the column is. The deflection of 1.33 is right here in the middle. So for this particular calculation, or this area, your area would be whatever is the, because this one is sloped in this direction as well. So in, is it survey? Is it in surveying where if you have, for example, four sides, and then if this elevation is 0, and then they say this is minus 1 inch, this is minus 3 inches, and then minus 1 inch as well. So all you have to do is to determine the volume of this one is you get area, right? To get the area and then the average height. So your average height is 0 plus like absolute value here is 1 plus 3, and then divide by 4, then that's your average height. Then times the area, now you have a volume. So that is for volume 1, and then times 4 because you have 4 locations. Then this area as well, this area, so this area and this area is the same, right? So you have three sides because this is the same elevation because it's sloping that way, right? So you have whatever, this is 0, this is 0, this is 0, and this is what, 6. In this particular example, this is 6. So this is minus 6. So 0 plus 6 plus 0 is 6, divided by 3 is 2. So the average height is 2 times the area of the triangle. So that's your volume. Say volume 2. Volume 1 is, this is 6 also. This is, say, this is minus, or this is 0 as well. And this is 0. So the same is 2 times this area. And then in this particular location, in this, so in this particular area, it will look like this one, right? Oh, by the way, this is not zero. I'm sorry. This is the 30 millimeter. This is the 30 millimeter surface tension. This is also 30 because you still have that surface tension like that. I think in the National Building Code, it is 30 millimeter from the lowest point of the opening. So that's 30 millimeter. This is 30 millimeter as well. And then in this particular area, it will look like this one. This is 30 millimeter, and then this is convert like 1 1/4 inch, and then this is I think that 8 something. So whatever is the area, then this will be your surface area, and then surface area, and then get the average height. So this one plus this one divide by two. So that's your total volume, and then times two because that's the same on this side. So your total volume, your total volume would be, volume of this one, volume one times four, then volume two times two, then volume three times three. So that's your total volume of what we call this one, total volume of possible, maximum volume of your funding load, like maximum water accumulation. But you have to compare that one with the what we call this one, the maximum daily precipitation times the area, and then whatever is the volume. Say, for example, for the sake of discussion, the calculated volume of this one, of your roof, is say 10.5 cubic meters. And then your precipitation, which is 89 millimeters times the area, it will end up, say, 9 meters or 9 cubic meters. Therefore, at maximum precipitation, water will not come out of the scupper or your discharge your in in hydraulics, that's spillway or something, whatever you call it, but in architectural, that opening is fully scupper. If that is the volume from the precipitation is less than the calculated volume of your roof itself, then you have the option is either use this one or use the maximum, this one here. And then if ever your 89 millimeter times the area of your roof exceeds this one, that means portion of the part of the water is already draining away from your roof through this copper. Then that's the time you will use this one maximum. So to be safe, when I do funding calculation, I'll just use this volume, and then um, automatic. I mean, I will not do calculation for this one. I will just go straight with this volume, whatever is the volume, and then that's my weight of the um that would be the cross section. So, for example, your roof, it will look like this one, your load. So this is the 30 millimeter, and then whatever is this is low here. Now, if that's the case, from pressure, which is gamma times height, so pressure of water is what? 62.4 pounds per cubic foot, then times whatever is the height. No, let's just, this one is pounds per cubic foot, and then times, the height here, times the height with divide by 12. This is in inches, say for example is 0.75. Then whatever is that value, that's your weight here. And then right here the same, 60.4 times, equivalent of 30 millimeter in feet. Then that's your height here. So for example, this is, for the sake of discussion, this is 10 psf, and then this one is say 20 psf, just for the sake of discussion. So this is your funding load. Now you include that in the load combination. This is in lieu of your snow load. So it's either snow load or this funding load. And then if your snow load, if your snow load is in this particular example, you calculated what how much was that? We still have the um open. The snow load here is 48.9. So 48.9. So therefore, because this one for your funding load, the maximum is 20 PSF. That means that is almost less than half. I mean, that's just a sample, so it's less than half. But if ever this value exceeds this one, say this is at 60 PSF, right? Even if this is a 30 and this is only 60, so this one is less than this one, but you have a triangular distribution, you have to calculate like both, like, check for snow load, like uniform snow load, and then check also for the funding. So you will have to have a separate load combination. If you are using a software, then you cannot just rely on the automated load combination. You have to do your own load combination to include funding load. And then the load factor for snow load per in BCC is 1.5. So that would be the same for funding load. So 1.5 um, load factor. So that is how you calculate the funding load. Now in the roof framing plan, so in our example, this one here, so it really depends on how the architect would lay out the roof drain so that you will have the less amount of insulation to bring the slope, unless because sometimes the roof truss are just flat, and then it is the insulation that will do the slope. Sometimes it is the joist itself or the roof truss is being sloped. So typically for this one, we slope the joist. So you have the top chord for the bottom chord flat, but the top chord of the truss is something like that one, you know, sloping top chord. It's either wood or this is a if this is a joist, like top bearing joist, top chord bearing joist, then this is usually flat, and then just slope the trusses itself, and then so that's why it's important to have the architectural drawing as well, and then ask for what is your roof layout. Sometimes they will have a roof drain here, then another roof drain here, and another roof drain. So that means it will go something like this one, or something. So the slope would be like that, or sometimes it will be like this one. I know this one would be half of that, and then it will be sloping that way. So it really depends. So just check the architectural plan. It should show the slope, the roof drain locations, and from there you can determine or you can calculate the volume the way we uh, do it ourselves, sample calculation, the way we do it here. So um, in the framing plan, in the framing plan, you have to show the actual funding load now, because if you are not the one who size the, so for example, typically here, um most engineer of record of the building will just show roof framing plan. Now this is the roof framing plan, and then it will be sent to a truss manufacturer, and then they will design the truss itself. Now, if that's the case, you have to show all your loading, including the bonding load. So in the roof framing plan, you have a, usually what we'll do is we will draw something like this. So for example, for the sake of discussion, this is our slope, like lowest point right here. So we will label this one, say this is 10 PSF, and then this is 20 PSF. So that's the bonding load. And then if it's this different in other direction, then you have to indicate, or if it's different in this location, then you have to indicate the bonding load. But you have to show the actual bonding load, so you can include that in the what do you call this one, in the um or the truss manufacturer can include that in their calculation, in their design of the joist. I don't have a, I don't think I have a copy here. I have a sample. Maybe in the next video I will show you really quick of a drawing where the bonding load is showed, like bonding diagram. I don't think I have a copy here, but yeah, like I said, once we, if I can, if I won't forget, but yeah, next video when we discuss when we discuss this loading, the wind load, because we will devote like a one full video, like separate video of this one, because I will be discussing the, in conjunction with the design load criteria that I sent out to everybody in the group, for that is that design load criteria for steel building, I think. So we will compare our calculation, or we will do a calculation and then compare it with, how it is done in the design load criteria. So once we do the video for this one, the wind load, then we will I will show you, I will put a reminder in my phone to get that file and then show you the bonding load diagram that you have to include in your roof framing plan. So I think that's it for today, and then see you in the next video.